So this will be the first of 10 videos you'll be watching in regards to this course, Mechanics of Motion. And so this first one is from Chapter 2, which deals with motion in one dimension. And so first off, we have, in terms of two quantities, we have distance, and then we have displacement. And so distance, basically, then, is the total distance covered. Whereas displacement, basically, is the straight line distance between two points. So in regards to that, then, let's say I have a point A and a point B, and I want to go from A to B. So first off, we first go in terms of this path that gets us to B. And so the total measurement of all that curve would represent the distance covered. Okay. Whereas the displacement would be the straight line from A to B. And so the blue line would represent the displacement. Okay. And generally, the distance will most likely be greater than the displacement. The only time where they would actually both be equal to each other is if the distance and displacement were both a straight line between point A and point B. Well, in regards to covering that, we can then look in terms of how fast did that happen. And so you get in terms of velocity. So velocity, or speed, books use them interchangeably, is given by the displacement divided by the time. Okay? And in physics, we will measure our displacement, our distance number, in meters, and our time will be in seconds. So velocity will be measured in meters per second. And then average velocity. So if you think in terms of if you drove here to the Art Institute, you would have that however many miles it was from your home to here, and the time frame it took you, and if you do that little division, you could get your average velocity. And that probably sometimes on the trip you were going faster than that speed, and sometimes you were going slower than that speed. So basically this will be then the final position minus the initial position, so the distance you traveled, divided by the total time. And that will give you your average velocity. In terms of equations then, we get that velocity is going to be the change in position over the change in time, which will be x minus x naught over delta t. X is the final position, x naught is the initial position. You can also look in terms of your instantaneous velocity, and instantaneous velocity is how fast are you going basically at any given point in time. And so one way you do that if you're driving your car is you just look down at your speedometer and you find out how fast you're going at that moment. And so you do that very quickly, and so basically we do this when this delta t is very, very small. So if you want to know how fast you're going when you're driving down I-5, you don't decide that you're going to look at your speedometer for the next minute. and see what your speed was. If you do that, you will either run into somebody or you will probably drive off the road. And so you want delta t to be basically 0 when you do that. Well, you can also look in terms of acceleration, which is then your change in velocity over your change in time. So velocity, we said, was in meters per second. Time will be measured in seconds, and so acceleration will be meters per second squared, per units. So first, a little bit about units and the units that we will be using. And the basic measurements are in terms of length, mass, and time. The base unit of length we'll be using will be meters. Mass will be in terms of kilograms. And then time will be in terms of seconds. And those will be the units we'll be using throughout this course. Well, in the chapter, you really then deal with these equations that let us figure out what's going on with an object that is moving. And so you get this set of equations dealing with the motion of an object. Right? And so we have the one we had up earlier, v equals x minus x naught over t. A, which is the change in velocity over the change in time. The average velocity, which we had up earlier, which is going to be 1/2 v plus v naught. And then we can have in terms v is equal to v naught plus at. X, the position, is equal to the initial position, v naught t, 1/2 a t squared. And then v squared equals v naught squared, 2a delta x. Right? So in terms of all those equations, you have that x naught represents the initial position, which will be in meters. X then is the final position, which will also be in meters. V naught, is the initial velocity, which will be in meters per second. V is the final velocity, which is also in meters per second. A is the acceleration, which will be in meters per second squared. And then t is the time, which will be in seconds. So those are the equations we'll be using and what all the various letters stand for. So in terms of those equations, all of those equations you should be able to take and then basically rearrange them and solve them for any variable. And so, given this equation, given that v squared equals v naught squared plus 2a delta x, we want to solve this for a. Right? I'm going to solve that for the acceleration. Right? Well, the way you solve an algebraic equation is you always do the opposite operation. So we have our original v squared equals v naught squared, 2a. Here we're adding v naught squared, so we will subtract. And so we get that v squared minus v naught squared is equal to 2a delta x. Well, 2a delta x, this means 2 times a times delta x. And so then the opposite of multiplying is to divide. And so we divide by 2 delta x. We divide this by 2 delta x. And so we get that a will be given by this. Okay. So we've taken our equation and we've rearranged it and we've solved it for a. And so for any of those equations, you should be able to take each one of those equations and be able to solve it for each of the variables that are there. Okay. So then you get to the hard part of physics, which is, okay, I got all of these equations that we get. The problems we're working on were basically word problems, and so you have to go through the words, and then you got to figure out, okay, which one of these equations do I use in order to solve the problem? And so in your book, also you'll find in the notes from this lecture that the book gives you a multi-step approach as to how to solve a problem. And we'll basically be using that in order to go through some questions. And so this first question comes from out of your book, and it's from chapter 2, and this one is problem number 12. And so basically you have one car here which is going at 88 kilometers per hour. And then we have a truck which is also going in that direction. And the truck is traveling at 75 kilometers per hour. And the distance in between the two is 110 meters. Right? And the question comes down to is, how many seconds will it take for the car to catch the truck? Right? So again, this is my car, and this is my truck. Right? Right. So we want the car to be able to catch up to the truck. Right? Well, first off, let's look at what we have here in terms of our problem. Well, we got that the velocity of the car is 88 kilometers per hour. The velocity of the truck is 75 kilometers per hour. And the distance in between the two, my x, is 110 meters. And what I'm looking for is a time frame. Okay? So we start out by listing everything we know and what we want to find. Now we need to check our units. As I said before, the units we're going to be using are in terms of kilograms, meters, seconds. And so we find that these two numbers here aren't going to work. So we need to change them from kilometers per hour to meters per second. And so you have, from the handout you get, that with the page of conversion factors, we find out that the conversion factor here is to multiply by 0.278. So I multiply both of those numbers by 0.278, and we get that this will be 24.464 meters per second, and this will be 20.85 meters per second. So we have in terms, now everything is in the right units. Well, what do we know? We know that we want that the distance that the car travels is going to be equal to the distance that the truck travels. And then we want to find the time for when that is going to be true. So we're going to use this, and let me keep those there for the moment so we'll have them handy. So we got the distance the car travels is going to equal the distance that the truck travels. So basically, in terms of equation, in this particular problem, there is no acceleration, and so we could look in terms of this equation. This term goes away because a is 0, and so we're going to look in terms of this equation. Right? So the distance that the car travels will be given by its velocity times the time, which will be, so that term there. And so we get, this will be 24.464 t. The distance that the truck is traveling is that it has a 110 meter head start, and it's going at 20.85 meters per second times t. And so we can take this equation now, and we want to solve this for t. And again, the way you solve an algebraic equation is by doing the opposite operation, and so we will subtract 20.85t, subtract 20.85t, and so we get 3.614t is going to equal 110, and then we divide by 3.614 and divide by 3.614, and we get that t is going to be 30.4 seconds. And so it'll take 30.4 seconds for this car to catch up to my truck. And so you get in terms of how to go through and solve a problem. Well, so you get in terms of this chapter, basically we'll be dealing with things that have undergo constant acceleration. So you notice in terms of my equation there, we have nothing where there's anywhere where there's any kind of change in A. So this chapter deals with just constant acceleration problems. And so a prime example of constant acceleration is gravity. So if you drop an object, the gravity pulls on it at a constant rate. So in terms of gravity, you have that the acceleration, which in terms of gravity is denoted in terms of g, and that number is 9.8 meters per second squared. And gravity always acts in just one direction, and that is always downwards. Okay? So in terms of our components, so velocity and gravity, they actually are vectors. They have a directional component to them. Okay? And for a lot of it, what we're going to be doing is that directional component will be in terms of is it positive or is it negative. Generally, in terms of velocity, we would probably think in terms of going to the right is positive and going to the left is negative. And then in terms of acceleration in the y direction, we would think of going up is the positive direction and going down is the negative direction. So in terms of gravity, how about something like this? So how long does it take for an object to drop 100 meters from rest? So eventually I have an object, whatever it is, and we're holding it there, and then we let it go, and it's going to drop, and we want it to fall 100 meters, and we want to know what is the time frame. Okay? So we're going to say my initial position, y naught, is 0. The final position is my 100 meters. My acceleration is g, which is 9.8 meters per second squared. And given that we dropped this from rest, we also know that v naught is 0. Okay? So we have those equations from earlier we had up, which was x equals x naught plus v naught t plus 1/2 a t squared. I can take that same equation and rewrite it in terms of y's. And if I do that, we just get y equals y naught v naught t plus 1/2 g t squared. Okay. Same equation, just in terms of y's. So now we want to find how long did it take for this object to drop 100 meters. Well, if I look at that equation, well, y naught is 0, which means that term goes away. V naught is 0. That means that this term goes away. And we end up with just y equals 1/2 g t squared. And it's that equation that we will actually be using in the lab that deals with free fall. And so now I want to take that equation and I want to solve it for t. So the way I get rid of the half is to multiply both sides by 2. So we get 2y equals gt squared. And then we want to divide by g. So we get 2y over g equals t squared. And then the opposite of squaring a number is to find the square root. And so t is going to be equal to the square root of 2y over g. And now we can take our numbers. So we get 2 times 100 divided by 9.8. And we find out that this will take 4.52 seconds for my object to drop 100 meters. So let's look at another problem involving gravity and what happens. And so now we'll look in terms of this problem. So given an object, is thrown straight upwards with a velocity of 34.2 meters per second, how high will it be after 2.1 seconds? And we'll call this part A. And then there's a second part to the question, which is what will be its velocity at that point in time? And what is its velocity. Right? So we got two parts that we want to find out for this. Right? So we have our question. Right? And so now again we want to look in terms of what do we know, what do we want to find, and then find the equation that we can use to solve this. So basically we have our object, we throw it straight up with a velocity of 34.2 meters per second. And when we do that, it'll go up to a certain height, whatever that may be, and then it's going to come back down. Okay? Well, what's acting on my object? Well, what's acting on my object is gravity. Gravity is pulling it down with a acceleration of 9.8 meters per second squared, and that's actually in the negative direction. Okay? After all we said earlier, that when we talk about y direction, that we're going to say going up is in the positive direction, going down is in the negative direction, and so gravity is always pulling downwards. Right? Right? So, we know that V naught is 34.2, change that, is 34.2 meters per second. Okay. And we know the t is 2.1 seconds. We know that gravity is pulling down at a rate of 9.8 meters per second squared. And we want to know in terms of y, and we know y naught is 0, our starting point, and we want to find y, which is how high up is it. So we go back to the equation we had in terms of the left, y equals y naught, v naught t, 1/2 g t squared. So in this equation, this problem, y naught is 0, which means this term goes away, and so we get y equals v naught t, 1/2 g t squared. So now we can take our numbers and plug them in. So we get y equals 34.2 times 2.1 plus 1/2 times g, which is a minus 9.8, times 2.1 squared. And if you plug all that in, we end up that my object will be 50.2 meters above the ground at that point. So that's the answer to part A, how high is it? Now the second part, what is its velocity? Well, for that equation, we can use that V equals V naught plus AT, and of course A in this case is my gravity. So V naught, we know, and so we get V equals 34.2 minus 9.8 times 2.1. And that'll give us 13.6, and that will be in meters per second. So we know what its velocity is at that time. Okay? So we know how high up it is at a given point in time. We know what its velocity is at that point in time. So if you think about this equation, if I think about what happens here with my object when I throw it up. As it goes, as soon as I let it go, gravity starts pulling it down. So I throw it up, and then gravity starts to pull back down on it. So if you think in terms of I take my keys, I throw them up, it goes up with a velocity, but as it goes up, that velocity slows down. It gets to its highest point, where for a brief moment that velocity will be 0, and then it starts coming back downwards. And so if I look at this equation here, and we'll see this particularly when we get to the next chapter, that we can find how long the object will go up in the air. So if I take this equation, v equals v naught plus at, and I solve it for t. So minus v naught, you get v minus v naught equals at divided by a, and we get v minus v naught over a equals t. So if we think in terms of this object and going up, we know that at the highest point, when I throw an object up, that v is going to equal 0, and so we get a minus v naught over g is going to equal the time to go up. And I'll leave this to you, but you get that this would then be a minus 34.2 divided by a minus 9.8, and that would give you the time up, which should be somewhere on the order probably around 3.6 seconds or so, if you were actually doing that out. So then we'll get to one last problem dealing with this motion of an object. And so we get to this problem. So we're standing on a cliff and we drop a rock. And that rock falls into the ocean, and then we hear the sound come back from when it splashes down. And so this is question 45 out of the book. And basically you have this. We're standing on a cliff. We have a rock, which we're going to let go and it drops. You have the water below. And they tell you, what we want to know is, how high is the cliff? So how high is the cliff? That's the question that they're asking. How high is this? Right? Well, what they give you. They tell you that the velocity for the speed of sound is given at 340 meters per second. They give you that in the problem. And they tell you that the total time for the event is equal to 3.2 seconds. And that total time means for the time for the rock to drop and it to splash down into the water, and then for those sound waves to come back up and you hear them. So that's what they're talking about in terms of total time. Right? So we don't know the time frame for the rock to drop. We don't know the time actually for the sound to come back, but we do know the total time of the event. So let's say that the time for the rock to drop is given by t. Okay? So that will be my time for the rock. Which means then that the time for the sound to travel is 3.2 minus t. Okay? So basically, this would mean that if this takes 2 seconds to hit the water, it would take 1.2 seconds for the sound to come back. And we know that it has to equal the sound. Well, we know that the distance that the rock drops has to be equal to the distance the sound comes back. So the distance the rock travels has to equal the distance the sound travels. So we know in terms of our scenario, we're going to say that the initial position of my rock is 0. We're holding it there, so the initial velocity of the rock is 0. And so we have, from the equation we've seen before, that y equals y naught v naught t 1/2 gt squared. And the distance the sound travels will be, will actually be a very basic equation. It's just going to be velocity times time. Well, y naught is 0, v naught is 0. And so my distance here will be just given by this. And so we just get over on this side that this will be 1/2 gt squared. And for my sound, this will be the velocity, which was 340. But then the time for the sound to travel, we said, was given by this, 3.2 minus t. Okay. So we get in terms of this. So we have 1/2 9.8 t squared equals 340 times 3.2 minus t. So we want to solve this for t. Well, half of 9.8 is 4.9, so we get 4.9 t squared equals 340 times 3.2 is 1088 minus 340 t. And let's make this a little better. Okay. So if I look at that, that is a quadratic equation. And in order to solve a quadratic, we want to first set it equal to 0. So I need to take these two to the other side. So we're going to add 340t, add 340t, subtract 1088, and subtract 1088. So we get 4.9 t squared, 340t minus 1088 equals 0. So now we have our quadratic, and it's equal to 0. Now the way we solve something like this is by using the formula. So we go back and we look at the quadratic formula. So the quadratic formula was based on your general quadratic, which was in the form of this. Okay. And then you had x was equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Where a was the number in front of the square term, b was the number in front of the x term, and c was my constant term. So, in terms of our particular problem then, we would have that A is 4.9, B is 340, and C is negative 1088. So now what we need to do is to take all the numbers and we plug them into our equation. And so instead of x, we're actually finding t, and so we get that t will be minus b, which means all it does is it changes the sign on this. So minus 340 plus or minus the square root of 340 squared minus 4 times 4.9 times a negative 1088 all over 2 times 4.9. So now it's a matter of doing some number crunching here, and we get a negative 340 plus or minus 340 squared, which is 115,600, plus 21324.8 divided by what would be 9.8. And if we continue our number crunching here, we can add what's underneath our radical. And so we get a minus 340 plus or minus the square root of 136,924.8 divided by 9.8. And this will be a minus 340 plus or minus 370 over 9.8. And so now you get, in terms of quadratic, you get, generally there could be up to 2 answers. And so there are going to be 2 possible answers here. One answer would be from that t is going to be the minus 340 plus 370 divided by 9.8. And that comes out to be 3.06 seconds, okay? The other answer would be possible if we were just talking in terms of just, this is just a quadratic, and it really wasn't anything physically happening, would be given by this. But this one would lead to a negative time frame, and so that can't happen. So my answer here is that t will be 3.06 seconds. And now that we know what the time is, we can figure out how high the cliff is. So we said for the rock, the distance it has to travel is given by that. And so we get that y is going to equal 1/2 times 9.8 times 3.06 squared. And we get that the cliff is 45.9 meters. And with that, that will conclude Chapter 2.